Okay, so yeah, so we're going to start out with just kind of a big overview of all of the immune system. And so when we look at our immune system in general, we need to look at kind of all of our levels of defense and all of our levels of immunity. So the innate immune system, pretty much the idea here is that it's non-specific. We have the same response to any invader, depending on what it is, okay? Bacteria, virus, anything, it's going to be the same type of response. And we just, there's certain cells and certain things that will attack those things, okay? This is definitely the first line of defense in our innate immune system is to just not let stuff in, right? To block things from coming in, right? So those are all of our surface barriers, right? Like our skin and our mucous membranes, all these parts of our body that are they're facing the outside world, or at least they interact with things that are open to the outside world. So that's our first line of defense, right? And then second, if something does get in, then we have internal defenses to kind of contain that infection, right? So those would be our phagocytes, so macrophages being an example of those, neutrophils being another example of those, cells that can engulf things, okay? We talked about the natural killer cells a little bit already, okay? In the process of inflammation, we'll talk about today, kind of walk through some of the steps of that, okay? We have certain antimicrobial proteins, and then the process of fever is all a part of this as well. Okay, so that's kind of our innate system, and we'll talk about some details here in a sec. But then secondly, we have, well, really our third line of defense is what's called our adaptive system, which is we have a very specific response directed towards a specific thing that got into our body, okay? And so we'll talk about this in a second, but for every new thing that we interact with, a new virus, right? How many people got a cold over spring break? Yeah, we had a few, not too many. Okay. There's been lots of colds going around, right? That's a new virus that you got, right? So then your immune system adapts and creates cells and creates antibodies that are specifically designed to deal with that virus and that virus only, right? And then that adds it to your list of hundreds of millions of viruses that you can specifically respond to because you've been exposed to that many viruses over the course of your life, right? And so next time that same virus comes in, those same cells that were trained against that virus that time, now they're gonna attack that thing, and you're not gonna get the cold the second time, right? Because your specific immunity, your adaptive immunity is ready for that virus to come in and deal with it very well. So there's two levels of that. The first level of that is called humoral immunity. So humoral immunity, humor means fluid, right? So this is the immunity happening in our blood, okay? This is what our B cells do. And what our B cells do is they make antibodies, okay? That's really what we're trying to activate when we get a vaccine, right? We get a vaccine, we're activating our adaptive immune system, and then now we have antibodies against that, whatever that thing is, okay? And then the other part of the adaptive immune system is cellular immunity, which is our T cells. Okay, the video talked about T cells a little bit there. One specific type of T cells called the cytotoxic T cell. We'll talk about how those work more on Friday, but they pretty much can go in and find a cell that's infected by the certain bacteria or virus, or whatever it is that they're looking for, and then cause that cell to destroy itself. So, and these are our lymphocytes, right? These T cells and B cells are our lymphocytes. Okay, questions on that little overview so far? So first line of defense is just make sure nothing gets in. Second line of defense is when things do get in, then we have our innate system to respond to that in the same way it would respond to anything. And then third line of defense is we have specific tools and weapons against every little thing that's ever been introduced to our body, and that's our adaptive system. So the immune system is one of the most complex and least understood parts of our whole body. And it's really remarkable and incredible in so many ways. Probably just next to the brain, it's the least understood part of our body is our immune system. Okay, so few things here just to look at both innate and adaptive. So on the innate side, again, it's non-specific, attacks all foreign invaders. It doesn't have a memory, right? We don't get a better innate response the second time something comes in. Okay, this is where fever and inflammation come from, is from our innate system. Okay, uses lots of phagocytosis, natural killer cells, and these antimicrobial proteins. If we look at the adaptive side, this is key. We need multiple exposures, right? The first time something comes in, we don't have a very strong adaptive response. We'll have the same innate response, but our adaptive response isn't very strong unless it's the second or further time. And then again, these two primary weapons here are the cytotoxic T cells and then the antibodies created by the B cells. And there's definitely some overlap between the two of them. They're not completely separate at all. So, okay, so let's look at kind of the basics of the immune system. One of the primary basics here is defining what an antigen is. Okay, so an antigen is any substance that can mobilize the adaptive defenses of the immune system. And really, the easiest way to think about it is it's an antibody generating substance. Okay, so something gets into your body and causes your immune system to make antibodies against that, then it's an antigen. That's what it is. Okay, so an antigen, or sorry, an antibody generating substance. Okay, we have some antigens that are part of our own cells, right? So we have self antigens. Okay, and these are called MHC, or major histocompatibility complex. You can just know it as MHC. But if you think about that term, it makes sense, right? Histo means what? Tissue, right? Yeah, tissue. And then compatibility, right? So it's just checking. These are things that help our immune system know whether or not this tissue that just came into our body is compatible with our body or not, right? And that's what that means, okay? So the function of these, this is how the immune system distinguishes self from non-self. Okay, and there's two primary types of these MHCs on our cells, okay? MHC1s are little proteins expressed on all cells in an individual, except for our red blood cells. They have some different ones we've already talked about, right? The A and the B and the O, or in the RH. Okay, but all other cells have these MHC1 proteins / glycoproteins sticking off of the cells, okay? And these, kind of like to think of these as either some kind of like an ID card that would tell some authority figure that you're a citizen of this country, or you're supposed to be here for some reason, right? You have the right to be in this place, okay? And that's pretty much how these act, because the immune cells are then going to go around and check our cells to see if they have these MHC1s on them, and see if those MHC1s match the ones that they're looking for. And if they do, fine. If they don't, the immune system attacks and destroys that cell. Right. So MHC1s are really kind of like those, yeah, that like citizenship of some sort, anything that kind of showing that those cells are supposed to be in the body. And then MHC2 is a different type. These are only expressed by by our immune cells, by our white blood cells. Okay, so these are kind of like a law enforcement ID, right? So they've got the regular MHC1 complex, a white blood cell does, but it also has this kind of law enforcement ID as well that kind of sets them apart, makes them kind of the enforcers of checking to see if people are supposed to be there or not. Not people, but cells. Okay, and this is all genetically inherited. There's millions and millions of combinations, so this isn't a simple thing like the red blood cells with just a few options. There's many, many different ones. Okay. All right, questions on any of this so far? Okay, so antibodies. So antibodies are also known as immunoglobulins. Okay, and these are part of our normal plasma proteins, right? Remember we talked about in our blood, one of the components of our blood is just the proteins that are always floating around in our blood. The primary one's called albumin, right, that we talked about. But then we have a bunch of these antibodies floating around all the time too, okay? And so if you guys remember back to the COVID days when we were just starting to figure out what was going on with COVID, there was like a sense where people wanted to like check and see if they had got COVID so they could get an antibody test. How many people remember that? Yeah. Did anybody go get an antibody test? Because like, I think I had it, but I never got tested. Did anybody do that? Yeah, I did that because I was just into that. Yeah, I did that because I was interested. I think we wanted to go to Hawaii or something. At that point, there was something that was like, you can go to Hawaii if you've already had it, or I don't know, something like that. But I thought for sure I'd gotten it at that point, and I hadn't, but I got it later for sure. Like probably all of us did. But yeah, so antibodies are the things that are created by the immune system to go against whatever came into our bodies, right? And so these immunoglobulins are made by the B cells. Okay. And the function of these is to bind to the antigen and then either inactivate it so it can't infect one of our cells or just destroy it. Usually have these kind of Y-shaped type structure with a little stem, and that Y shape gives it the ability to bind to kind of two different antigens at the same time. And then by doing that, it creates these big clumps in the blood, and that kind of inactivates and mobilizes these antigens from being able to go and bind to anything else. Okay, so it's definitely part of the adaptive system. And take a quick guess there on that clicker question there on top. Is just asking how many different, very specific types of antibodies can an adult produce? By the time you get to adulthood, how many unique antibodies and unique antigens have you responded to typically?
Yeah. Like I have a class that like a guy
Say it again.
I sent you the link.
Thank you.
With the
Appreciate it.
graph so you can check
That's
it out.
great. I love that. Thank you. All right, go ahead and send that in if you haven't yet. All right. That's the most active clickers I've seen in class for a while, 68. That's pretty good. Only got two or three. Yeah, I guess three. 69, even better. Wow. Okay. All right. So 70% of you are saying C, which is not the right answer. D is the right answer, but you're just guessing, so no big deal. But think about that with me. So we're talking about 1 trillion different things that have entered our body by the time we're adults, right? 1 trillion different unique things. And that's amazing in and of itself. But then the fact that our body has actually created weaponry against every single 1 trillion of those things. And if any of those come back in, we've got the stuff ready for it, right? And that's how our immune system works. So it's just kind of mind-blowing to think of that vast of a number of unique weapons that our body has built against things. One of the problems with our society today is that there's the theory called the hygiene hypothesis that says that we're probably too clean these days, right? We probably bleach too many things and clean too many things. And so throughout childhood, we don't actually interact with enough of these things anymore. And so our immune system doesn't actually get trained like it used to, when the parents used to just let the kids lick the ground and stuff like that. And that's just very normal for kids to do. But maybe the ground they're licking has just been bleached so many times, there's nothing there anymore, right? And so there's a huge spike in the number of autoimmune disorders, which is pretty much our immune system turning on our own bodies. And part of that is probably due to the fact that looking like that that we just haven't trained our immune system enough in the early years. And so then when it does get kind of a novel antigen exposure later on in later childhood, or even in the teenage years or even the 20s, that can end up kind of making the immune system go haywire, and then it turns against some cell of our own body, right? So for example, like peanut allergies are way higher than they ever used to be. Type 1 diabetes is way higher than it used to be. Pretty much all autoimmune disorders have increased in prevalence by massive numbers. And most of those are probably triggered by some kind of thing coming in, like it could be a virus or something else. And then your body creates an immunity against that. But then that antibody actually fits part of our body too, like our beta cells of our pancreas, and then it starts destroying our pancreas as well. That's how type 1 diabetes works. So so there's something really interesting going on there that they're trying to figure out. And actually, to that idea, they figured out that like allowing babies to eat peanuts or peanut butter within the first year of life drastically decreases the risk of having a peanut allergy. And so it's something about that for sure. So yeah, questions about any of that? Okay. All right, so let's talk about some of these cells. So the T cells, T lymphocytes, these are part of the adaptive system, okay? Part of the adaptive system, part of what's known as the, sorry, I don't know why that did that. Can't seem to zoom out now. It thinks my finger is the stylus. Try this one more time. Okay. Yeah, here we go. So, yeah, so adaptive cell-mediated response, okay, not the ones that create antibodies, but the other ones that use cells to attack things, okay? The life cycle here is they are made in the bone marrow, like all of the cells are, but then they mature in the thymus, and that's where they get the T part of their name, because they mature in the thymus, that organ that's around our throat, okay? Their function is to recognize an antigen in combination with that MHC protein we were just talking about, and then they activate the immune response. And there's 4 primary types that we'll talk about. Most importantly are the helper T cells. The helper T cells are the ones, when it showed, that video showed the macrophage coming and showing a piece of the bacteria to something in the lymph node. That was a helper T cell, right? The helper T cell is the one that activates all of our adaptive system. Okay. But then then you saw the T cell kind of dividing and other cells coming off of it. Some of those cells that are created off of it would be cytotoxic T cells. Those are the ones that are going to go out and actually try to find that bacteria and destroy it. There's regulatory T cells that kind of slow down the activation, and memory T cells that just automatically go into storage, and they're ready for that antigen to come in again the next time. And when it does, then we've got machinery ready to go. Okay, so those are our T cells. Our B cells are, again, also part of the adaptive system, but then specifically the humoral response, which is meaning that we're putting a bunch of stuff in the blood. Okay, so these ones are made in the bone marrow like the other ones, but they mature also in the bone marrow, and that's why they're called B cells. Okay, so they mature in the bone marrow, and then they get sent out into the bloodstream, eventually find their way into a lymph node, and that's where they take up residency. Okay, the function of these is to make antibodies. Okay, each only produces one type of antibody. Right, so again, when we make 1 trillion different antibodies, that means we have 1 trillion unique memory B cells just sitting in our lymph nodes waiting to be activated. Okay. When we call them a plasma cell, all that means is that antigen that they're trained to go against was introduced to them, and then they made their way back out into the bloodstream and started releasing antibodies. So a plasma cell is the activated version of a B cell. B cell that's in the bloodstream dumping out antibodies like this one. Okay, questions on any of this so far? Go ahead, Wesley. Yeah.
I have a question. So, like with a mother to a child when they're like developing, do they get some less immunization, or do they like once you come out, then it starts getting things?
Yeah. So there's definitely during breastfeeding, the in breast milk there's antibodies, and so whatever antibodies mom is producing goes into the breast milk, and baby gets that. As far as during fetal development, there's not much happening there as far as transferring of immune properties, just because the blood doesn't like fully mix. There could be some antibodies that make their way over, but probably not. But the baby's so protected at that point, right, that there's really nothing that's actually interacting with it. But as soon as they start getting breast milk, then for sure they're going to get antibodies for exactly whatever mom is dealing with, right? And I think I mentioned that one before, that yeah, mom interacts with the virus, she's going to make antibodies for it and give it to baby right away, and the next round of breast milk, pretty much that baby will be able to fight that virus. Yeah. Okay. All right, so let's take a quick minute here. We kind of already talked about these leukocytes, but this was back in the composition of the blood. So just do a quick review of these and see which one those were. There was a table like this at the end of the blood composition notes. So pull that one up and just, yeah, walk through, just typing in the cell name here, and we'll come back together in a sec. Yeah. Oh, yeah.
Is it like, we're required to go for the whole time, or is it just part of it, or like, I don't know.
I mean, ideally, you'd go to the whole, do you have something else going on?
Well, I was just about to dinner with like friends later, but like I want extra credits.
Yeah, I mean, yeah, you're expected to be the whole thing. Yeah. 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 Yeah.
I would have stuff, I just kind of put out here and ends at 7.
Yeah.
Okay.
Yeah, that's fine. Yeah, so, yeah. Yeah. There'll be like a little survey that you fill out pre and like before and afterwards, so,
Okay.
yeah. All right, let's go ahead and walk through this just as a little review here before we dive into some specifics with the immune system here. So phagocytic, the cell that's usually going to have the first contact with something is those neutrophils. That's because they're just so prevalent. There's just so many of them in the body. Okay. The ones that are specifically helping us kill virally and virally infected and cancer cells. Which one was that? Yeah, those are those natural killer cells or NK cells. Okay. The ones that are going to turn into macrophages, those are called monocytes. Okay. The ones that destroy invaders, clean up debris, stimulate the adaptive system, they're an APC, which means an antigen presenting cell. Okay. These are those macrophages. Okay. The ones that release histamine, which one was that? Mast, there we go, mast cells, thank you. The other major APC, antigen presenting cell, ones that roam around the body, those are all called our dendritic cells. Now, these are the ones we've been talking about this class again. Ones that make antibodies, which ones are those? B cells, which are the ones that activate the B cells and the T cells. Helper T cells, and then the ones that actually do the killing as far as the T cells go. Yeah, the cytotoxic T cells, and then we've got our memory T cells, and then we've got our regulatory T cells. Okay, so lots of different cells involved in the immune system here. And these would be our white blood cells, right? Our leukocytes, which makes up a pretty small percentage of our total blood cells, but that's just because there's so many red blood cells, right? Okay, questions on any of these before we keep going? Okay. All right, so let's talk about some specifics of the innate side of the immune system, and then Friday's class we'll talk about the adaptive side. Okay, so obviously again, that first line of defense is to block things from coming in, right? So the skin and the mucous membranes are key for that, right? We've talked about all this stuff. We have these keratinized cells on our skin, which are just like packed with protein. That's all that's left, just like this little protein coating, right? Also oils on our skin. The mucous membranes have certain chemicals that will catch things and not destroy them or not let them in. Okay, so we have all of that. Part of our innate defenses is our chemical defenses that are also on our skin. Okay, viruses infect a cell by taking over a host's kind of metabolic machinery to reproduce themselves. Okay, so viruses get inside of a cell, and then they pretty much take over the nucleus of the cell, cause that cell to start replicating the virus itself, right? And so when a cell gets in that state, when it gets infected like that, it starts releasing something called interferons. And interferons are one of those examples of cytokines, like the video talked about. And what they do is they get sent out by that cell. That cell's like, I'm in trouble. I got taken over by a virus. So save yourselves, pretty much, right? It starts sending out these interferons, telling all the other cells in the area to watch out. There's a virus in this area. And then those cells that get stimulated by those interferons put up pretty much like a shield around themselves and have this blocking proteins that don't allow that virus to attack them. So that's another example. And then another thing that happens is complement proteins. Okay, we'll talk about complement proteins a little bit more when we talk about antibodies as well. But these, again, are just part of our proteins that are floating around the blood at all times. But just like our blood clotting process, if we just activate one of those, then it starts this whole cascade and eventually creates these little proteins that will circle up like this and poke a hole in cells, right? And it just creates these little pores in cells, which then that makes the cell's contents spill out and the cell gets destroyed, right? So this is a very effective part of our immune system in activating the complement protein to form those pores of a cell that's already infected. And then that cell lyses, and that also stimulates other immune cells in that area. Okay, questions about any of this so far? Give you a sec to finish writing that down. Okay. All right, so that's kind of the non-cellular component of the innate system, right? Things that are just blocking things that are proteins that can become activated, but it's not cells, right? So then the next part of the immune system is the cellular part, right? So which are the cells that are helping us do this? So we've already talked about those neutrophils, right? They're very mobile, they're floating around through the blood all the time, they're phagocytic, they're the most abundant. And so when they interact with something like a bacteria, a virus or something, recognize that it's not supposed to be there, they'll engulf it and destroy it, right? Our natural killer cells are somehow going around looking for virally infected cells or cancerous cells. And most of the time they're recognizing that those cells are not healthy, and they're causing those cells to destroy themselves, like that video we watched a couple times ago. Okay. Mast cells, again, these are cells that when they get activated, they release a chemical called histamine, and histamine is what stimulates the inflammatory process. We'll talk about details of that in a second. How many people took a Claritin or a Zyrtec or an Allegra today? Yeah, antihistamines, right? That's what all of those are. Those are all antihistamines, blocking one or more of the histamine receptors in your body. And then macrophages, these are similar to neutrophils, but they're just bigger, and they have all kinds of other weaponry that they can use to destroy things. Respiratory burst is pretty much like a big free radical release that these macrophages do that can destroy kind of everything in the area. Okay, and these are infecting things, foreign cells, bacteria. They also come in after an injury and help clean up any debris from an injury and things like that. Okay, so we're going to talk about the inflammatory process. Okay, so as you go along in your studies, into nursing or whatever you might be heading into, we'll definitely take some classes where you talk about the 4 classic signs of inflammation. Okay, and these are heat, redness, pain, and swelling. Okay, so if you see those things on your body somewhere, then you know you've got inflammation in that area. Right, so it gets hot, you can feel it, it's hot to the touch, turns red. There might be some extra fluid in that area, and it hurts. Okay, the 5th one that's kind of added more in fields of like physical therapy and occupational therapy is impairment of function. It's not necessarily one to consider one of the classic signs, but usually you got some stiffness or some rigidity or some weakness to that area as well, which would lead to a decrease in function. Okay, so what we're going to do is kind of walk through what activates this whole process. And then the key thing for you to understand here will be like, what is causing each of those 4 cardinal signs of inflammation? Okay, so when we get hurt, we can use that example that was in the video where it showed like a splinter coming into the skin, right? A splinter was like poking through the skin, goes through, okay, that damages some cells, right? That splinter goes right through some of our cells, makes them burst open, right? Damages some other tissue. And what happens with that is those damaged cells and the mast cells in the area will release that chemical called histamine. But then they also release other things. Everything that's inside of the cell, a cell that gets damaged gets dumped out too. And both the histamine and the cell contents have a way of activating our immune system. Okay, so histamine is a vasodilator. That's what it does. It causes your blood vessels to relax. And so we get more blood going to that area, right? So that's going to lead to both heat and redness, right? Blood is warm, okay, and it's red, right? And so when we get more blood going to an area, our skin in that area becomes warmer and it gets hot, or that's the same thing. It's warmer and it gets red. Okay. And then other chemicals that come from the inside of our cells activate nociceptors too. And nociceptors, remember, were our pain receptors. Okay. So certain things that spill out of the inside of our cells directly bind to pain receptors, and that hurts. Okay. Vasodilation is going to then cause, when we get that vasodilation that happened from the histamine, that then causes increased delivery of white blood cells, right? Neutrophils, monocytes are going to turn into macrophages. Those, we get a bunch more of those because we got more blood coming to that area. And then it also helps because we get clotting substances that end up there too, right? It might kind of seem weird to send more blood to that area, but when we send more blood to that area, we get all the help that we need by the stuff that's in the blood, right? And clot the blood, we can get the cells there, they're going to help attack whatever just got in, okay? But then vasodilation is also helpful because it can carry away the stuff that we don't want to be there too, right? We got to kind of increase circulation to kind of move stuff out, right? And then another thing happens called increased capillary permeability. Okay, so the chemicals, including histamine and others that were released from the broken cells, cause our capillaries to kind of open up a little bit more, right? We looked at those capillaries last time and how the water can leak out, right? It does leak out. When we have certain chemicals released, it actually makes the endothelial cells spread apart from each other a little bit more, and there's bigger gaps between the cells, and so that means more stuff can leak out. And so we have increased capillary permeability. That means more fluid's going to get out into our interstitial space, which also means that all these cells can get through there and get out in the interstitial space. So we get fluid, proteins, leukocytes, all of that stuff can get into the interstitial space now. And all of that can be helpful to help us get the stuff there that we need to deal with whatever the injury is. But that also leads to swelling, right? Because we're adding extra components to the interstitial space. So we're increasing the osmotic pressure there, which then pulls water with it. And that's what causes swelling. Okay, so we're kind of getting to see where the heat and the redness and the pain and the swelling come from right here. Okay, questions on this so far? Okay. Continuing with this, couple nice images from your textbook here that kind of show the same idea. Okay. We also have increased phagocyte migration, which is also known as chemotaxis. Okay. Chemotaxis means that we have a bunch of cells kind of aggregating to a certain area, right? So when that splinter got pushed into our skin, had some bacteria on it, had something on it that activated some macrophages or some neutrophils, they release all those cytokines. And then those cytokines activate a bunch more immune cells to come to that area, to come where the problem is, right? And that's chemotaxis, is when all those cells aggregate right there in that area, okay? We also get fibrin formation. Talked about that last or a couple times ago whenever we talked about blood clotting, right? So we get a lot of clotting happening in the area. And then we get pus too, right? So when we have some kind of a wound that eventually gets some white buildup underneath it, we call that pus, right? And this is really just all this stuff that was sent there that's now dead, right? So a bunch of neutrophils, a bunch of dead bacteria, other debris from that injury. That's really what's in that pus. Okay. Questions on this? Okay. All right. Well, let's do this clicker question here. Talk with the people on your team about it here. It's to choose all that apply. How often do you get care packages when you go on? Okay, yeah, that's, I was gonna say, that's special, very special. Let's go. Yeah. Victor, can you actually send me that little printout of my thing too? Does that happen? Yeah, see? Yeah, cool. Yeah, send me that. All right, go ahead and send it in if you haven't yet. Maybe try hitting the send button on this type of question. All right, we're missing like 5 people, it looks like. Make sure to hit the send button. All right. Okay, so pretty much everybody's saying both A and B. Okay. The first one's obvious, right? If we're activating nociceptors and we got pain, okay, so some of the stuff inside of our cell, we actually have something that comes out of our cells called substance P, called that because it stimulates pain. That's one of the things. But there's other things too, like hydrogen ions stimulate this, calcium can stimulate this when there's too much of it coming out. Yeah, so definitely that. Pressure caused by swelling, for sure. If we get too much fluid in a space, that can actually activate our pressure-sensitive nociceptors, okay? Blood clotting, probably not so much, but I would make the case for vasodilation being related to this because we wouldn't have much swelling without vasodilation. We wouldn't have so many immune cells come into the area because they also release chemicals that can activate pain as well. So vasodilation is related to this for sure. And then chemotaxis too, right? Because of those immune cells that get brought to the area, they're going to release certain chemicals that also will eventually lead to pain as well. So I'd say all 4 of those, but A and B are the ones that are for sure, for sure. I know you guys love vagueness and gray areas. I just do these questions in class so you have something to talk about, right? But yeah, Julia. Perfect way to say it, Julia. Yeah, yeah, kind of indirectly causing pain, whereas A and B are kind of directly causing pain. Yeah, thank you. Okay, other questions on this? Okay, so this next thing is just kind of like a little flow chart that I put together that you can kind of use to map this out, okay? And so what I'd like you to do is kind of work with the people on your team here and starting with the injury of the tissue of some sort. Again, we're talking about that splinter coming in. That can be a good example. What's our main stimulus? I'll open up that one. It's going to be histamine and then cell contents, okay? And then you can kind of see with where we're going, like this stuff's all leading to increased blood flow. This stuff's all leading to different stuff being allowed to enter the interstitial space. This one is related to migration of cells. So that can kind of give you an idea of what we're looking for. And so the 3 main responses are here, and then in red are the signs of inflammation. So just kind of talk through that, see how much of it you feel like you can fill in with those blanks. And then let's answer this question, which is just like the last one, but instead of pain, it's swelling. Okay, so go ahead. Talk through that with the people on your team.
And it's like, if we don't get them back, I'm gonna call them, say we're working for them. People really come to my business. So wait, I I don't know information that I that's what I've always wanted. Like all the. I've never taken this. I've taken it to like LA and even though it's. Yeah. And he's been saying the phone.
Pretty good with your finger. Pretty neat.
My
Did it
pencil's
die?
dead and I don't have the adapter. I
Oh,
dropped it in
yeah.
my.
Oh, you can't plug it in over here?
You can, but it like comes off. It's not the same.
It's a different
No.
kind, yeah, like the newer version, yeah.
Were you writing with your finger?
Yeah, she was, it was like perfect.
Oh.
Yeah.
Oh, there's an arrow. Oh, there's. Because they go. That's the
All right, so you're sending in your answer to that clicker question up there in the top. Which of those would lead to swelling? Again, make sure to hit send with that type of question. All right, about 5 more people, it looks like. Go ahead and hit the send button if you haven't yet. Good, I'll leave it open for a sec just in case, but okay, so yeah, most of you are saying A, B, and D, and then about a third of you are also adding C in there. But yeah, so which leads to swelling? Definitely vasodilation, right? We're sending more fluid, more blood to the area, more of that can get out and leak into the interstitial space. Um, it can come out of the vessels more if our capillaries are more permeable, right? So that's definitely a key thing. The blood clotting, probably not. It's kind of the opposite, right? Like the faster the blood clotting happens, then the less swelling we're going to have, right? But then chemotaxis for sure, because that just means more stuff coming, right? More cells coming to the area. It's just going to end up with more stuff out there in the interstitial space that's going to lead to some swelling. Okay, so let's talk about these three. Yeah, talk about the things that aren't filled in here. So what did you guys put for this one here? The one that's going to lead to increased blood flow. Vasodilation, got it. Okay. And then, yeah, and then from there, allowing things to enter the interstitial space. That one's got to be the capillary permeability. And then what do we call this? This migration of leukocytes and phagocytes. Which one? Chemotaxis, yeah, for sure. Oh, yeah, there we go. Pain and then chemotaxis, for sure. Okay, so those are kind of our 3 big things happening that then are going to lead to the other things that eventually lead to the signs of inflammation. Pain was just directly caused by either histamine or other chemicals, right? So that's why it didn't have like a chain of events. Chemo, yeah. So then let's go back over here to vasodilation. We get increased blood flow, and then that was going to lead to 2 of our cardinal signs of inflammation. What were those? Heat and redness. Got it. Perfect. Okay. And then with that increased blood flow, that's also going to help us clear stuff out of the area that we don't want there, but it's also going to deliver stuff that we do want there, right? So both things. And then blood clotting is obviously a part of that as well. Okay. And then with the chemotaxis one, we got leukocytes migrating to the area, and then that's going to also be a part of the swelling process. The fluid accumulation is a part of the swelling process. And then you got this weird arrow that is making its way over to swelling there from increased blood flow somehow, but it is. Okay. And good job. As I was walking around, I was really hearing a lot of you kind of work through that and come up with that. And that's what this is for, just to give you an opportunity to digest it and work on it. So questions on any of this? Okay. All right, let's talk a little bit about fever. So fever is due to systemic inflammation of some sort, meaning inflammation throughout our whole body. Okay. Our body temperature is maintained by our hypothalamus. Okay, which is really serves as kind of like this thermostat in our body, right? It's like a thermostat in your house. You set it to a certain temperature. If it goes above that, the AC turns on. If it goes below that, the heater turns on, right? Same idea with our hypothalamus, okay? Normally we're somewhere right here around 98.6, although we did find out during COVID when billions of people were taking their temperature every day that it's actually lower than that now. If it actually changed, we don't know. If actually the measurement technique changed, we're not sure. But I think average temperature, body temperature is about a full degree lower than that, actually. It's what we kind of discovered during COVID with all that data coming in of everybody's temperatures all the time. But yeah, if we're too cold, then we increase our metabolism. That helps us warm up. And we can also shiver if we're really cold, because then we just contract our muscles in a really, really inefficient way. And it's all lost as heat. Okay, so fever is caused by these things called pyrogens. Pyrogens are chemicals that are released either by the microbes themselves that got into our body, or by macrophages, or by neutrophils. These are the primary cells that are going to release that. And what they do is they actually interact with our hypothalamus and change the set point in our brain. Right, so they change the set point. They increase the set point. Bless you. And so the way this works is you're at 98.6, let's say, okay? You get an infection. Those pyrogens go up to your hypothalamus, kind of dial up the temperature to where now your set point is 100 degrees instead. All of a sudden you feel cold, right? Even though you're 98.6, but you feel cold because your brain's telling you you're colder than your set point. That's when you get the shivers, right? When you're sick, right? When you've all had that, when you get a fever, you're just feeling cold. You can't quite get warm, okay? And then you warm up, right? Then your body warms you up, okay? And so that's kind of why you get the chills. But then most of us will take a Tylenol or an ibuprofen, something like that. That actually blocks those pyrogens, makes our set point go back down. But now we're already up high. Then what happens? We sweat, right? How many people have been sick with a fever and you wake up in the middle of the night and your whole bed's just soaked with sweat, right? Yeah, that's because you broke your fever, right? It's because then your set point got turned back down and then your body cools you down by sweating, right? So you kind of just go back and forth like that a lot when you're sick. But the reason for fever is it can be helpful because it can help directly kill microbes. It can reduce iron levels in our blood, which makes it so certain bacteria can't multiply as well. And so it can help us that way. So really it's a question like, should we actually take that Tylenol or the ibuprofen? It really is symptomatic relief for sure. And the fever can actually help us fight that thing off. So if you're just laying in bed anyways, maybe just suck it up and deal with the fever. But most of us don't like the feeling of it because it's very uncomfortable, right? And so we take those drugs. But yeah, a couple other things that can be a problem here. If the fever lasts too long or the temperature gets too high, we can hurt ourselves, right? And kids in particular have much poorer temperature regulation. They can actually go into what's called a febrile seizure, which can your brain doesn't function too well above a certain degree, and that can be potentially harmful as well. So that's it, guys. Have a great rest of your day. We'll see you on Friday. Is what? Oh, yeah, that's a good question. My guess is